So in part two, we are going to continue to talk about what a derivative is. But what we're going to do is we are just going to think about a little bit of a new notation. So a little prime symbol next to the function means that we have done this derivative. It is called differentiation when we do that. So you'll hear that word used. You can see we have the derivative here as x gets closer and closer to a, will give you that slope of that tangent, or we have that difference quotient as that h gets 0, we're getting closer and closer to a, we're getting to be a tangent. Now both of these are formulas for the slope of the tangent. So you will see that both of those formulas used. Most of the time we're going to rely on the difference quotient one, because this one doesn't always work well with some functions. Sometimes it works good for polynomials because you're able to factor them, but other functions I would definitely stick with 3.6. So let's practice some more of the things we did yesterday. So now what does this mean? Well, this means our a is going to be 2. Okay, so let's think about what is f of x. Well, that's just 3x squared minus 4x plus 1. What is f of 2? Well, 3 times 2 squared is 3 times 4, or 12. 2 times 4 is 8. So 12 minus 8 is 4, plus 1 is 5. So we know that f of 2 is 5. So if we want to find the slope of our tangent or our derivative at an a value of 2, that is just going to be the limit as x approaches 2 of f of x minus f of 2 over x minus 2. Now we know what f of x is, we know what f of 2 is, so let's plug those things in. So we're going to get 3x squared minus 4x plus 1 minus f of 2. Now if it was negative, I would definitely use parentheses, but it's just a 5, so we could just minus 5. Now let's simplify that as much as we can. So we're going to get 3x squared minus 4x minus 4 over x minus 2. If right now we would try direct substitution, we would get 0 over 0. Now remember, if we have a limit that gives us 0 over 0, that means it's a removable discontinuity, and you can remove the discontinuity at that point by just reducing it down, fixing the problem. So that top function is factorable. If we factor it, take a look, we get a negative 6 plus 2 is going to give us that negative 4 in the middle. 3x times x is 3x squared. Positive 2 times negative 2 is negative 4. So we have everything we need. And you can notice that our factor in the bottom that was causing the issue is going to cancel out. So we can just take the limit as x approaches 2 of 3x plus 2. Now that function allows us to use direct substitution. So we can just plug in 2. So we get 6 plus 2, or 8. So I know that the derivative at 2 is equal to 8. I can also say that the slope of my tangent at 2 is equal to 8. They mean the same thing. Sometimes for just the derivative, it's just for the sake of doing that algebra. Sometimes we actually want it for the equation of a tangent line. It depends on what we're doing. Now here, we're going to do the same exact thing, but we are going to use the difference quotient formula, formula 3.6. So we need to find f of a plus h. Now remember, a is 2. See here where the a is? That's just a 2. Okay. So let's find what is 2 plus f of 2 plus h. What is f of 2? So that we can have something to put right here and right there. Okay. If I plug 2 plus h into my function, I get 3 times the quantity of 2 plus h squared minus 4 times 2 plus h plus 1. Yep. Okay. We already found f of 2 on the last slide. F of 2 was 5. Make sure. Yes, f of 2 was 5. Okay. So the one we have to do the most work for is f of 2 plus h. Now what's technically happening here is you're kind of going to fix the algebra, and that's why the difference quotient up front seems a little more complicated, but in the back end it's a little easier. But anyway, so if we do 2 plus h squared, that's really 4 plus 4h plus h squared. Now let's distribute. We get 12 plus 12h plus 3h squared minus 8 minus 4h plus 1. We're getting there. We're almost done. And then if we combine like terms, we get 3h squared plus 8h plus 5. Okay? Okay. Now let's stick those into the formula. So here we're going to put f of 2 plus h minus f of 2. We're going to put right there. Watch what happens. So the derivative at 2 is the limit as h approaches 0 of f of a plus h, which is just 3h squared plus 8h plus 5, minus f of 2, which we found to be 5, all over h. Now, what's going to happen is our 5's are going to cancel. If you did it right, the difference quotient will tell you at this point, both things on top should be divisible by h, so we should be able to divide off the h. So we get the limit as h approaches 0 of 3h plus 8. And now we can plug in 0. If we plug in 0 for h, we get 8, which is exactly what we found on the last slide, that our f of 2 was equal to 8, or our slope of our tangent is 8 at the point of a being 2. So different formulas give us the same exact value. So here it says to find the derivative at the number a. So we're just going to leave a in the formula. Feel free to use either formula. It doesn't really matter which you use. Because it's such a nice polynomial, sometimes the other formula works nice. It is going to be factor, but you're going to have a's in it. So let's just do our difference quotient. So we need f of a plus h. We need f of a. F of a is just a squared minus 8a plus 9. So that one's the easy one. The f of a plus h usually requires work. So we have a plus h squared minus 8 times a plus h plus 9. Well, a plus h squared is a squared plus 2ah plus h squared. Distribute the 8, and then plus 9. Now, at this point, there's nothing that we can do. It's just one big, long thing. Okay, so we're going to write f of a plus h, a squared plus 2ah plus h squared minus 8a minus 8h plus 9. And then we're going to subtract f of a. So put it in parentheses. All over h. Now, at this point, do not do anything with the limit as h approaches 0 until you have simplified the top as much as possible. So watch what happens on top. So I still have to just have this big old list. I'm going to distribute the -1, and then I'm going to look for things that'll cancel out. So usually what should happen is anything that does not contain an h to cancel out. So my a squareds cancel, perfect. My -8a and my +8a, perfect. My +9 and my -9, and you'll notice that everything else contains an a, so that should check your work. So write down everything else you have. You have a 2ah, an h squared, and a -8h. Now it's all over h, so now you can check if you're right. If you did your algebra right at this point, the h should be divisible into every single piece. Just divide it. So it's going to be 2a plus h minus 8. And all we're going to do is we're going to plug in 0 now for the h only. And we get 2a minus 8. So the derivative of x squared minus 8x plus 9 is 2a minus h. And we could use that to find the slope of the tangent when a is 1, when a is 2, when a is 7. So by just leaving a generic a there as a placeholder, we can find a formula for every single slope of every single tangent line for any point on the curve. Now, derivatives are actually denoting a rate of change. So if we just take 2 points, let's say our function is a time, and when we stick in a time, we know the distance we have gone. So it becomes a distance over time. So if we just go between 2 points, that is the average velocity over some time interval. But an instantaneous velocity is a derivative. So a derivative is just a slope of a tangent, or it is an instantaneous rate of change. So if a problem gives you 2 points, 2 x values, a starting x and a stopping x, you just find the slope between those 2 points. It's just a slope of a secant, and that will give you an average velocity. But an instantaneous velocity happens at one particular point. And you'll notice that if we have an equation for our distance formula, if we take the distance we have traveled, that s of t, so the notation is that s of t is our distance traveled. And if we take our derivative, that is going to be our velocity at a particular instant. Okay, so remember the difference between the two. Average velocity is just a secant slope. Instantaneous velocity is a tangent. So it says in this example, suppose that a ball is dropped from the upper observation deck of the CN tower that is 450 meters above the ground. What is the velocity of the ball after 5 seconds, and how fast is the ball going when it hits the ground? So here is our distance from the ground formula, I guess you could call it. That's the distance we're traveled if you drop a ball. So at 1 second, it would be 4.9 meters. At 2 seconds, it would be 4.9 times 4, and so on. So the velocity after 5 seconds, what we're pretty much going to do for A is we're going to find the derivative, and then we're going to find what happens at 5 seconds. So the derivative is going to be the velocity, and they've only mentioned that 1 5-second time, so it's an instantaneous velocity. So we need to find the derivative. So we're going to take the limit as h approaches 0. So we're just going to do s of t plus h minus s of t all over h. So the a's are a time of some sort, so we'll put t, and then the h is going to just be our generic h. Now if we put t plus h right here, s of t plus h is just 4.9 times t plus h squared. Which is 4.9 t squared plus 9.8 th plus 4.9 h squared. Okay, so that's going to go in the s of t plus h spot. It's going to be 4.9 t squared plus 9.8 th plus 4.9 h squared. And then we're going to subtract the function if we just have a t sitting there. So minus 4.9 t squared. Now you'll notice we are subtracting a 4.9 t squared. We have a 4.9 t squared. Everything else has an h in it. So it's just 9.8 th plus 4.9 h squared divided by h. If we divide everything by h, we get 9.8 t plus 4.9 h. Plug in 0 where the h is sitting. We get the limit as h approaches 0. Well, no, we can just plug it in. Sorry. So we're going to plug in 0, and we get 9.8 t. So now we have a formula for the derivative, or for the velocity at a particular time. Well, they wanted the velocity at 5 seconds. So the velocity at 5 seconds is the derivative at 5, or 9.8 times 5, which is 49 meters per second. So in part B, we are looking for when do we travel 450 meters. So t squared is 450 divided by 4.9. So t is the square root of that. Time, we're not going to have a negative time. And if we square root 450 divided by 4.9, we get at about 9.6 seconds, it's going to hit the ground. Now, it says how fast is that? Now, we have a velocity equation. Our derivative is our velocity equation. So the derivative when we hit the ground is just plug in 9.6. So 9.8 times 9.6, we are going 94.08 meters per second. Now, you will see that as we explore derivatives, we will be doing more and more things with velocity and acceleration and those kinds of physics applications. And that's where it became so useful. And let's go ahead and skip this one for now. When we explore some more applications for the derivative, we may come back to a problem like that later on. Okay, so that is your homework, and there you go.